Ever wondered how data is organized in databases? Today we dive into the fascinating world of relational data structures. These structures are like the backbone of databases, arranging data in a tabular format with rows and columns, quite similar to the layout of a spreadsheet. The concept of relational data structures was first introduced by E.F. Codd back in 1970, and since then, it has formed the basis for relational database management systems, or RDBMs. Understanding these structures is crucial not just for software developers, but for anyone who deals with databases. They are the building blocks that enable efficient storage, retrieval, and manipulation of data. From tables to keys, indexes, views, and constraints, these structures provide a flexible and effective way to manage structured data. Ready to explore how these structures work and why they are so important? Let's get started. First off, we have tables, the backbone of any database. Dive into the realm of databases and you'll discover a world organized in tables. Picture a table as a two-dimensional structure, a neat arrangement of rows and columns. It's much like a grid, with data nestled in each cell. Each row in this table represents a single record or entity. Think of it as a line item in a ledger or a single entry in a diary. Every row is unique and holds information about one specific entity. Then we have the columns. Each column is like a category that describes an attribute or field of the records. For instance, in a table of books, you might have columns for title, author, genre, and publication year. Each column brings a different facet of the record into focus, giving us a comprehensive view of the data. Together, these rows and columns create a relational table. Each table typically corresponds to a different entity or concept within the domain we're modeling. In a library database, for instance, you might have separate tables for books, authors, and borrowers. Each table stands on its own, but they're all interconnected, forming a complex web of relationships that mirrors the real world. But don't be fooled by their simple layout. Tables are powerful tools. They make it possible to store vast amounts of data in a structured, organized manner. They allow us to retrieve specific pieces of data quickly and efficiently, to sort and filter the data in countless ways, and to analyze the data to uncover patterns and insights. In the world of relational databases, tables are the workhorses. They're where the data lives and breathes. They're where we begin our journey into data modeling, and they're where we return to again and again as we navigate the vast seas of data. So, in essence, tables are the fundamental building blocks that hold our data. Next up, we have primary keys and foreign keys, the glue that holds our tables together. Primary keys and foreign keys are essential tools in the world of relational databases. They work together to maintain order, establish relationships, and ensure data integrity across multiple tables. So what exactly is a primary key? A primary key is a unique identifier for each row in a table. It's like the fingerprint of a table row. No two are the same. This unique identifier is a column or combination of columns that helps us pinpoint a specific record without confusion. It ensures that each row in the table is uniquely identifiable, providing a reliable reference point for other tables to latch onto. Now, imagine we have another table that wants to reference the data in our first table. How can it do that? This is where foreign keys come into play. A foreign key is a column or set of columns in one table that refers to the primary key in another table. It's like an outstretched hand reaching towards another table, creating a bridge or relationship between the two. This relationship enforces what we call referential integrity. What does that mean? Simply put, referential integrity ensures that the relationship between two tables remains consistent. If a row in one table references a row in another, then the referenced row must indeed exist. It's like a promise that the database makes, saying, if I reference something, it's definitely there. These relationships that primary keys and foreign keys create can take various forms, like one-to-many or many-to-many relationships. For example, in a one-to-many relationship, a single row in one table can be related to multiple rows in another. On the other hand, in a many-to-many relationship, multiple rows in one table can be related to multiple rows in another. In essence, primary keys and foreign keys serve as the connective tissue of our relational databases. They enable us to link disparate pieces of data together, creating a cohesive, interconnected web of information. Primary keys and foreign keys are crucial in maintaining order and relationships in our data. Indexes and views, two powerful tools in our data management toolbox. Let's dive into indexes first. Imagine you're in a library looking for a specific book. Without a system in place, you'd have to go through every single book until you find the one you're looking for. Now imagine if the library had a catalog, an index, that guides you to the exact shelf and spot where your book resides. That's essentially what an index does in a relational database. Indexes are special lookup tables that a database search engine can use to speed up data retrieval. Simply put, an index is a pointer to data in a table. It works on the same principle as the index in the back of a book, presenting you with a sorted list of the key fields of the table rows and where they can be found. Indexes can be created on any column of a table, but they're particularly useful on primary keys, foreign keys, or columns that are frequently referenced in your queries. While indexes speed up data retrieval, they do take up space and can slow down the time it takes to update the table with new entries. Therefore, it's a balancing act between retrieval speed and storage space. Now let's talk about views. A view is essentially a virtual table. It doesn't hold any data of its own, but instead it displays data that's stored in other tables. Think of it like a filtered lens you're looking through to view your data. You can set up this lens to only show you certain columns or rows from one or more tables, or even show you the results of a complex query. Views can be really helpful for simplifying complicated operations, enforcing security by limiting data visibility, and providing a level of abstraction from the complex underlying data structures. In essence, a view is a stored query that you can treat just like a regular table. But it's more flexible and powerful because it can pull together data from multiple tables and present it as if it were a single table. Indexes and views, while not physically holding data, significantly enhance our data manipulation capabilities. Finally, we have constraints, the guards that ensure our data's integrity. Constraints are like the unsung heroes of relational data structures. They are the rules or conditions applied to the data we store, ensuring that it remains consistent and maintains its integrity. Without constraints, our data might become a wild jungle, full of inconsistencies and inaccuracies. Imagine a world where the same person could have multiple unique identification numbers, or where a product could exist in the inventory system without a name or price. It would be chaos, wouldn't it? This is where constraints come in, ensuring that our data behaves in a way that makes sense and follows the rules we've established. One of the most common types of constraints is the primary key constraint. This ensures that the primary key of each record in a table is unique and not null. In other words, there can't be two records with the same primary key, and a record can't exist without a primary key. Then we have foreign key constraints. These enforce the relationships between tables. They ensure that the data in a foreign key column matches data in a primary key column of another table. This way we maintain the integrity of our relationships. Unique constraints are another type we often see. These ensure that all data in a column or a set of columns is unique. For example, you might have a unique constraint on an email column to ensure no two users share the same email address. Check constraints are also quite handy. These let us specify a condition that must be true for each record in a table. For example, we could have a check constraint that ensures the price of a product is always greater than 0. So you see, constraints are the invisible forces that help keep our data clean and reliable. They enforce the rules and standards we set, making sure that our data is always in a state we can trust and work with. Constraints, though often overlooked, play a vital role in maintaining the quality of our data. So, we've taken a tour of the world of relational data structures. We've delved into the realm of tables, the core of these structures, where each row signifies a unique entity and each column an attribute. We've discovered the importance of primary keys in uniquely identifying each row, and foreign keys in establishing connections between tables. We've also navigated the world of indexes, the silent heroes that speed up data retrieval operations. Then we've looked at views, these virtual tables that present subsets of data or transformed representations, simplifying those complex queries. Finally, we've touched upon constraints, the rules of the game that ensure data integrity and consistency. All these elements together not only organize data but also make managing it a breeze. Understanding these structures equips you with the knowledge to effectively work with databases and manage data. Until next time, keep exploring.